so this video we're going to continue talking about static electricity in chapter 20. I want to talk a little bit about the way things, how we can charge things. There's two basic methods. One is direct contact. That's called conduction. Basically, if I hit charge by direct contact, let's suppose I have two identical metal spheres, exactly like. Now, metal is a really good conductor, so let's suppose that I have a charge of Q on this one, a positive charge, but this one's neutral. And I'm going to put a handle on these so I can, little stand. But my handle is an insulator. I want to be able to grab this one and pick it up, but I don't want to take any of the charge off. If I bring those two in contact, since like charges repel, all of this positive charge over here would like to get as far apart as possible. And so just by bringing them in contact, I will charge this one, and they'll end up with a charge of Q over 2 and Q over 2. So they'll each end up with half of the original charge just by bringing them into contact. Anytime you have a charged conductor and you bring it in contact with another conductor, that charge is going to redistribute as far as possible over the surface. If I wanted to draw this more pictorially, before they touch, let's suppose this had 1, 2, 3, 4, 5, 6, 7, 8. We'll let those 8 positive charges represent maybe a charge of 8 microcoulombs. Afterwards, those charges would spread out, and we would end up with 4 microcoulombs on each. Now, if I had a third one, let's suppose I had a third one. We'll call this one A, B. And again, this is A, B. If I have a third one, C, that doesn't have any, and I now bring B and C together, again, the charge will redistribute. In other words, the 4 microcoulomb charge here would now redistribute and leave them each with 2 microcoulombs. So that's charging by conduction, just allowing the charge to flow from one conductor to another conductor. Okay? There is another type of charging that does not require direct contact, and that's called induction. In induction, there's no direct contact. A really easy way to charge by conduction might be to have 2 conductors that are in contact with each other. Those 2 are touching, but it's neutral. This looks like a neutral rod. In fact, I'll leave it in 2 pieces. If I bring something positive near it, so I have a positively charged, maybe that's a plastic rod, but whatever it is, it's positively charged. This is a metal conductor. Well, in a metal conductor, we know opposite charges attract, so the electrons will flow over here. When you bring, I might get this really close. When you bring something close, so this side becomes negatively charged, well, this side will have an equal amount of positive charge. Basically, the charge just separates and the negative electrons flow over here. Well, if I suddenly separate those 2 pieces, this piece had a negative net charge, and this piece had a positive net charge. So I managed to actually charge both those pieces of metal, but I didn't actually touch them. Induction, I almost say, is charging by scaring. If I hold something positive here, it's like it scares positive charges over here and attracts negative charges over there. Okay, but there's no direct contact. Brings me up to another idea, and it's the idea of charge polarization. Before we get to that, though, let's consider. Suppose we have a thread, and on this we have a little teeny tiny ball that's negatively charged. Let's see how I want. Look at my picture. Well, let's start off be positively charged. We know that if I bring something negative near it, this string will swing over here to be close to it because opposite charges attract, right? So that makes perfectly good sense. We expect that to happen. If it had been negatively charged and I bring something negative, it'll swing away to get farther away. Again, that's what we expect because we know like charges will repel each other. But there's a mysterious thing that can happen. And this mysterious thing is charge polarization. What we find is neutral objects also are attracted to charged objects. Okay, we know opposite charges attract, but why does a neutral object feel attracted to a charged object? They're never repulsed, but they'll be attracted. So what happens then? Well, if I have something neutral, if I have a neutral conductor, and let's say it's hanging from a string, and I bring something close to it that's positive. Well, what happens is we know that in a metal conductor, charges are free to move. That attracts electrons over here, and this side becomes positive. So the charges actually separate. When charges separate, we call it charge polarization. Technically, this is still neutral, but because the charges have separated, the negative charges are closer, this will actually swing over here to get closer. Do that awfully close. So it will swing over to get closer because the negative charges on this side are attracted. So even though technically it's neutral, it does feel attracted. And we can see how if we have a conductor, it's real easy for that to happen. But it actually happens with insulators too. If I tore up a little piece of paper and had little bits of paper, it would actually be attracted to something that had an electric charge. So what's going on here, because we have an insulator, well, it turns out even in insulators, even though the charges can't flow, it's not like a metal where the negatives can come running and the positives stay over there. Most molecules are what we call polarized. One side of the molecule is slightly positive, the other side of the molecule is slightly negative. Water is an example of a polarized molecule. So what happens when you bring something positive or negative, just charged, even though this is neutral in here, the molecules that are in this little piece of paper, this little bit of styrofoam, whatever this insulator is made of, can shift just a little bit so that the negative side of the molecule is closer and the positive side of the molecule is farther away. technically you can tell it's completely neutral. But even so, when those molecules shift just a little bit, it makes this side of that bit of paper slightly more negative than this side of the piece of paper, and it'll actually be attracted, okay? Now, what never happens is repulsion. There's no way for something neutral to be repelled by a charge, because when you bring that charge close, charge polarization always says, the positive side will get further away, the negative side will get closer. So it turns out that we know that opposite charges attract, like charges repel, but also neutral objects can be attracted to charged objects. Okay. Now, anytime you feel something feels an attraction, whether it's or it doesn't have to be attraction or repulsion, that's a force. That's an interaction. In this case, with gravity, it was always an interaction between masses. Now this is an interaction between electric charge. Well, in 1785, there was a man named Charles Coulomb. And Charles Coulomb came up with a formula for how much force, the strength of this force or this interaction between electric charge. And his formula said that the force is equal to some constant K, Q1, Q2 over R squared. And that's the electrostatic force. Okay? If you look at that, it looks almost exactly like the gravitational force. Remember our gravitational force? It was equal to capital G, mass 1, mass 2, over R squared. We have different constants. This has a gravitational constant. This is a number we call Coulomb's constant. Gravitational forces depend on the size of the masses. Electrostatic forces depend on the size of the charges. Q1 and Q2 are the charges. And we measure those in a unit called a Coulomb, which is represented with a capital C. So instead of having masses in kilograms, now we have charges measured in coulombs. And of course, R is the distance between them. Okay. Notice the gravitational force was what we call an inverse square law. It's a 1 over R squared rule. And the electrostatic force is a 1 over R squared rule. We're not going to worry when we put in Q1 and Q2, we can just put in positive numbers. But we know that when these two signs are opposite, that's an attractive force. When these two signs are the same, that's a repulsive force. Okay? One of the things we'll just leave this for a minute because we're going to talk about it quite a bit. So what happens? So let's suppose we have two charges. Maybe this one has plus 6 coulombs, and this one has plus 6 coulombs. Well, it's really obvious that they would repel each other. They're both positive, and it's really obvious that those forces would be the same. Right? Okay. Well, it turns out they're going to be the same no matter what. When we calculate this force, it's this force, that force is acting on each object. So even if, let's do one, we had a situation where we only had a small amount of positive charge, same size object, but this object has a whole lot of negative charge. Well, This is an interaction between those two forces. They're going to be attracted to each other. And the degree of attraction is going to be exactly the same. If this is the force on the first charge and this is the force on the second charge, what we find is those forces are equal even though the opposite direction. The force on the one is equal to the opposite of the force on the second. Why is that? Well, Newton's third law. Newton's laws still apply when we talk about electrostatic forces. And it turns out that Newton's third law is really important. And it says the force of A on B is equal but opposite to the force of B on A. So even though they don't have identical amounts of charge, this interaction, this K, Q1, Q2 of R squared, is going to be exactly the same. So they're going to feel an equal amount of force. Okay. Hopefully that makes sense to everybody. We know that when we're talking about charges, really important, we haven't said how big a charge is, but it turns out that there's a quantity called the elementary charge. The size of this elementary charge was first discovered by a man named Robert Millikan. And the elementary charge, E, is equal to 1.60 times 10 to the negative 19 coulombs. It's a very, very small quantity of charge. Most of the time when we talk about electric charge, we're going to talk about quantities that are in the range of millicoulombs or nanocoulombs. They're very small, microcoulombs. This is a very small charge, but it's really an important number because that's the charge on one proton or one electron. The only difference, of course, is that electrons are negative. So the charge on a proton is equal to a positive E, or positive 1.60 times 10 to the negative 19 coulombs. The charge on one electron is negative E, or negative 1.60 times 10 to the negative 19 coulombs. They have equal but opposite charges, and it's a really small charge. We now know that if you have 1 whole coulomb of charge, you're talking about millions and millions of electrons. Something for one, whether it's if you're talking about a coulomb of negative charge. If you're talking about a coulomb of positive charge, you're talking about millions and millions of protons. Everyday matters, charges are going to be really small quantities. Like I say, millicoulomb, that's 10 to the negative 3. Microcoulomb, that's 10 to the negative 6. Nanocoulombs, it's 10 to the negative 9. Probably the only place that I can think of where we have charges that are truly in coulombs, if we think about something like a lightning bolt. Now, a lightning bolt might have 25 coulombs of charge. That's a huge amount of charge. But everyday problems, really very small. I'm not assigning any problems where you actually have to work out Coulomb's law as far as actual values, but I am going to give you some problems where I want you to understand how it behaves, because it behaves exactly the way gravity behaves. So I want to go back and look at Coulomb's law. So here's Coulomb's law. It says the force between two charges is K, Q1, Q2 over the distance squared. In other words, it's directly proportional to the charge, Q1 and Q2. It's inversely proportional to the square of the distance. What happens? Let's suppose that this is our original force. I have two charged objects. They're some distance apart. They're going to give me a force of F. I want us to understand what happens if we start changing parameters. So let's say I ask, let's see what I'm running over here. And it's going to basically be a game of what happens if. And our first if is going to be we double Q1. If I leave everything exactly the same, and this is my original force, my new force, and I'm going to put a little prime just to show it to you, is K 2 times Q1, because I doubled Q1, and I leave everything else alone. Notice this looks exactly the same, except I've got a 2 out in front. Now, if I pull that 2 out in front, we realize that if the only thing we change is we double one of the charges, it doubles that force. This force, F prime, is exactly 2 times the force we had to begin with. If the only thing I do is double this number, well, my force is going to get twice as big as it used to be. Okay, that makes sense. So if we double Q1, the new force, which I'm going to call F prime, is twice the original. It's twice what it used to be. I didn't have to double Q1. I could have doubled Q2. I would have had the same result. If let's go back to our original. This time, let's triple Q2. I'm going to leave everything else alone. Well, if all I do is replace Q2 with 3 times Q2, you can see that F prime is now going to equal 3F. Okay? So, increasing charges does exactly what you would think it should do. Okay? In fact, we could do both of those. If we double Q1 and we triple Q2, then my new force looks like this. We didn't change K, but Q1 we changed to twice as big. And Q2 we changed to 3 times as big. We didn't mess with the distance at all. Notice, what do you get if you multiply 2 times 3? Well, 2 times 3 is 6. You end up with 6K Q1 Q2 over R squared. This looks exactly like our original force, only larger by a factor of 6. So our new force is 6 times the original force. Now, honestly, I did those most. I just want you to, so you would understand how changing charge would affect something. But most of the problems about this are not actually about changing the charge. They're about changing the distance. So let's look at what happens if we change the distance instead. We'll start with just doubling R. We double the distance. Well, that means my new force, we didn't mess with anything on top here, but our distance is twice as big. We doubled that distance. Well, here's where we have to be really careful. 2r squared means 2r times 2r is 4r squared. If we double the distance, this looks exactly like it looked here, except for this 4 right here. This is equal to 1/4 the original force. Well, that makes sense. We would expect that if we pull charges farther apart, the interaction between those charges that are farther apart would be much weaker. Turns out that if we double the distance, the strength of that force is actually only 1/4 of what it was originally. Hold on, I'm just going to see if this looks important. It's all good. Okay, so let's see what happens if instead of doubling the distance, we triple that. Let's change that question. I'm going to write the answer to that part A there. We got that the new force was 1/4 the original, or you could write that F divided by 4 if you like. Okay. What if we triple the distance? Again, just practice. Put in what happens. We're not sure. Q1, Q2. We're going to replace R with 3R. They're 3 times as far apart squared. But we have to remember that when we take 3R times 3R, what we get is that this is K, Q1, Q2, over 9R squared. Again, it looks exactly like what we started with, except for that 9. So it turns out when you triple the distance, it falls to 1/9 the original force, or F over 9. That makes sense. As we get farther apart, it's going to get weaker and weaker. If we do 4 times the distance, well, 4 squared is 16, and this would be 1/16 the original force. Or if we made the distance 5 times as far apart, this would become 5R squared. It'd be 1/25. Okay, that's an inverse square law. Now, perhaps a little less obvious is what happens when we bring them closer together. Well, let's use some common sense here. This is not that tricky if you think about it. If doubling the distance makes it 1/4, then going the other way, halving the distance should make it 4 times as strong. If tripling the distance makes it 1/9, then making the distance 1/3 of the original, bringing them back together, should make it 9 times stronger. But I can show you with the math too. So, what will happen if we halve the distance? Our new force will be K, Q1, Q2. We're not messing with any of that. But this is going to be 1/2 of R, or R divided by 2 squared. Okay, that's half the distance. R over 2 times R over 2 is R squared over 4. So we're going to end up with this fraction in the bottom. Okay. If you remember learning to divide by fractions, go back to 6th grade. If I'm dividing by fraction, I could change that to K, Q1, Q2 times 4 over R squared. Remember how when you divide by fraction, you flip it? This becomes 4K Q1 Q2 over R squared. In other words, if I half the distance, the force gets stronger. How much stronger? 4 times stronger. Similarly, if I change that distance, and you can pause that if you want to study over that, but let's just think, because there's really a pattern that if we get the hang of, it's not hard. If we do 1/3 the distance, so now instead of being 3 meters apart, they're only going to be 1 meter apart. Again, we know if we go from 1 meter to 3 meters, the force becomes 1/9 the original force. So it makes sense if we go from from 3 meters down to 1, it should be 9 times stronger. Let's just put it in just to convince ourselves. K, Q1, Q2, this is our new force. This will be R over 3 squared. That's going to be R squared over 9. R over 3 times R over 3 is R squared over 9. When we flip this to multiply, this becomes 9K Q1 Q2 over R squared, which means our new force is 9 times the original force. So, if you remember doubles and triples, you'll probably be just fine. If you double the distance, you get 1/4. If you half the distance, you get 4 times as much force. If you triple the distance, you get 1/9 the force. But if you go to 1/3 the distance, you now have 9 times the force. That's the way these inverse square laws behave. I don't think I assigned you anywhere you actually have to plug in charges. I've done that in the past, but I'd rather you understand how the law behaves. I'm not very concerned about punching numbers on the calculator. Okay, so that finishes this particular video, and we're going to have another one over electric fields, and I think that probably is going to finish this chapter for us.